Surging waves conceal a world teeming with fierce battles for survival. Coral reefs, where vibrant schools of fish weave through the razor-sharp branches of coral. The dark depths of the deep sea, where bioluminescent creatures drift through eternal darkness. But who truly reigns over the ocean? The great white shark bursts from the depths, wielding a bite force capable of obliterating anything in its path. The orca dominates the top of the food chain in the world's most diverse marine ecosystem, with intelligence and unmatched strength. The Greenland shark lingers in the deep for centuries, outliving all other ocean giants. How much do you really know about the vast and mysterious ocean? Share your thoughts in the comments below. But for now, welcome to Ocean Predators, Clash of the Most Terrifying Giants. Most of us know that whales are the world's largest marine mammals. But do you know how long they live? The bowhead whale can surpass 200 years. The blue whale often reaches 90 years. The sperm whale lives for about 70 years. However, when their lifespan comes to an end, a whale's journey does not conclude as you might think. Its true journey is only just beginning. This is a cycle that has been sustained for millennia, known as whale fall. In 2009, a Monterey Bay Aquarium Research Institute research team discovered a whale fall at a depth of 1,250 meters at Clayoquot Slope. Even 14 years later, its skeleton remains the heart of an ecosystem, where hundreds of deep-sea species gather to make use of its remaining energy. In 2019, scientists found a whale carcass at Davidson Seamount, Monterey Bay, resting at a depth of 3,200 meters. Just 4 months after it had sunk, the site had already attracted crabs, fish, worms, octopuses, and various mollusks. An entire self-sustaining ecosystem emerged from the passing of a giant, transforming a barren stretch of the ocean into an oasis of life. The great and mysterious predators of the deep come to Whale Falls not just for a feast. They are the guardians of balance, ensuring that the cycle of life continues without end. Whale Fall, where what seems like an ending becomes the foundation for a new generation of life. The name ocean originates from Oceanus, the ancient deity in Greek mythology. The Greeks and Romans once believed that Oceanus was not a vast body of water, but rather a massive river encircling the world. Indeed, the ocean covers nearly 3/4 of Earth's surface. From space, the deep blue of the ocean dominates over the green and brown hues of the land. a colossal expanse of water stretching over 361 million square kilometers, embracing continents, surging through deep trenches, and carrying within it the origins of life on our blue planet. There is no definitive evidence pinpointing exactly when liquid water first covered Earth, but scientists have found traces of ancient oceans embedded deep within the planet's crust. At Isua Greenstone Belt, Greenland, a type of rock called pillow basalt, formed when lava erupts underwater, has been dated to 3.8 billion years ago. This means that water was already flowing on Earth at that time, and possibly much earlier. At Nuvvuagittuq Greenstone Belt, Quebec, Canada, some rock samples have been dated to 3.8 billion years old, while another study estimates they may be as ancient as 4.28 billion years. If oceans existed before this timeline, any evidence may have been erased by plate tectonics, the constant movement of Earth's crust that has reshaped the planet's surface for billions of years. A hypothesis proposed in 2020 suggests that oceans may have existed from the very beginning. According to this model, water did not arrive from asteroids or comets, but was already present in the materials that formed the planet. When the young sun was only 70% as bright as it is today, a thick atmosphere rich in greenhouse gases kept Earth from freezing, allowing liquid water to persist even with much weaker sunlight than we have now. Oceans have continuously reshaped, split apart, and merged through Earth's cycles. Plate tectonics, post-glacial rebound, and sea level rise have redrawn coastlines and ocean basins over billions of years. Supercontinents have formed and broken apart, from Rodinia to Pangaea, forcing oceans into new configurations. At times, a global ocean may have covered nearly the entire planet, with no land masses rising above the surface. During colder climate periods, ice caps and glaciers expanded, trapping more water as ice. This caused oceans to shrink, exposing new land. In contrast, during the Eemian interglacial, 125,000 years ago, when the climate was warmer, sea levels were about 5.5 meters higher than today. Going back 3 million years, in the Pliocene warm period, sea levels were even higher, possibly by 50 meters. This change is not just history, it is also the future. Global temperatures are rising. Ice in Greenland and Antarctica is melting at a faster rate than at any point in human history. NOAA and IPCC estimate that if all the ice at both poles melted completely, global sea levels could rise by 65 to 70 meters, submerging many of the world's largest coastal cities. Earth itself will not disappear due to climate change, but its shape will change, just as it has for billions of years. As of now, the ocean covers approximately 70.8% of Earth's surface and holds 97% of the planet's total water supply. If Earth were divided into two hemispheres, there would be a water hemisphere containing the majority of the ocean's surface and a land hemisphere where most of the continents are concentrated. This distribution divides the ocean into 5 major regions: Pacific Ocean, Atlantic Ocean, Indian Ocean, Southern Ocean, and Arctic Ocean. The largest ocean is the Pacific Ocean, covering 46% of the planet's total water surface. With an area of 165.25 million square kilometers, it is larger than the entire landmass of Earth. Its estimated volume is around 714 million cubic kilometers, accounting for 50.1% of the world's ocean water. Massive ocean currents swirl through its vast expanse, creating immense circulation patterns. The center of the water hemisphere and the western hemisphere both lie within this ocean. The oceanic pole of inaccessibility, the point in the ocean farthest from any land, also belongs to it. Point Nemo, located 2,688 kilometers from the nearest land, is closer to the International Space Station than to any human on Earth. The average depth of the Pacific Ocean is around 4,000 meters, but some locations plunge far deeper. Challenger Deep, in the Mariana Trench, is the deepest point ever measured on the planet, reaching 10,928 meters. Not far from it, Sirena Deep sinks to 10,714 meters, while to the south, Horizon Deep in the Tonga Trench descends to 10,823 meters. These regions lie beyond the reach of sunlight, where pressures exceed 1,000 times that of sea level, and temperatures are so cold that only the most specialized creatures can survive. Situated in the warm waters of the Pacific Ocean, the Great Barrier Reef is the largest coral reef system on Earth, stretching over 2,300 kilometers along Australia's coast. More than 1,500 fish species, 400 hard coral species, and thousands of other marine creatures thrive here, forming a vibrant and colorful ecosystem. The Pacific Ocean also plays a central role in global climate phenomena. El Niño warms ocean waters in the central and eastern Pacific, causing droughts in some regions and heavy rainfall in others. La Niña has the opposite effect, cooling ocean waters, leading to stronger hurricane seasons and unusual shifts in weather patterns. Smaller than the Pacific Ocean, the Atlantic Ocean covers 85.13 million square kilometers, accounting for 17% of Earth's surface and 24% of the world's ocean area. On the map, it appears as an S-shaped body of water stretching between two continents, divided into the North Atlantic Ocean and the South Atlantic Ocean by the equator. Some definitions extend the Atlantic Ocean's boundaries to Antarctica, where massive icebergs break off from the southern ice shelves and drift into the frigid depths. Winds and currents have turned the Atlantic Ocean into a circulatory engine for the planet. The Mid-Atlantic Ridge, the longest underwater mountain range on Earth, stretches over 16,000 kilometers, cutting through the ocean from north to south. This is one of the most geologically active boundaries on Earth, where the oceanic crust continuously expands, pushing young basaltic rock outward on both sides. At these locations, hydrothermal vents release towering black smoke plumes rich in minerals, sustaining ecosystems that thrive without sunlight, a phenomenon you will explore in the next part of this video. For now, the Atlantic Ocean is best known as the center of events that shaped human history. For thousands of years, it was seen as the greatest barrier between two worlds. The ancient Greeks called it Atlantis Thalassa, referring to the sea beyond the Pillars of Hercules, known today as the Strait of Gibraltar. To early explorers, it was an uncharted frontier, an ocean of mystery and peril. But in 1492, when Christopher Columbus crossed these waters, the Atlantic Ocean ushered in a new era, the Age of Exploration, a time when European powers like Portugal, Spain, France, and the United Kingdom used this ocean to expand territories, establish trade, and build colonies along both shores. The third largest ocean in the world is the Indian Ocean. Covering 70.56 million square kilometers, the Indian Ocean accounts for 20% of Earth's total ocean water. Situated between three continents, it embraces the ancient lands of Asia, Africa, and Australia. Its average depth is around 3,741 meters, but in certain places, the ocean floor plunges into tremendous abyssal depths. Seamounts and ridges formed by hotspots serve as evidence of this ocean's youth in Earth's geological history. Beneath the surface, the Mid-Indian Ridge, Southeast Indian Ridge, and Central Indian Ridge continue to expand, shifting the seafloor and creating underwater mountains and deep-sea valleys. As the warmest ocean on the planet, the Indian Ocean acts as a climate regulator for the world. Its climate is heavily influenced by monsoons, generating wind cycles that shape rainfall patterns and temperatures across vast regions. For thousands of years, the Indian Ocean has been a highway of civilizations. From dhows gliding across the waters from Arabia to India, carrying spices and gold, to the voyages of Portuguese, British, and Dutch fleets during the colonial era. The trade routes of this ocean were once the lifeblood of the maritime Silk Road, where commerce between Asia, the Middle East, and Africa flourished for centuries. Today, it remains central to global trade, particularly for oil and hydrocarbons, as major shipping lanes like the Strait of Hormuz and Strait of Malacca serve as key transit points for the world's energy supply. Meanwhile, the Southern Ocean is set apart from the rest of the world by powerful currents and the strongest winds on the planet. Unlike other oceans, whose boundaries are defined by continents and islands, the Southern Ocean is not confined by land. It is a continuously moving body of water, an endless vortex driven by the Antarctic Circumpolar Current, the strongest ocean current in the world, carrying approximately 173 million cubic meters of seawater per second around the Antarctic continent. With an area of 21.96 million square kilometers, the Southern Ocean is larger than the Arctic Ocean, but remains smaller than the Pacific, Atlantic, and Indian Oceans. The Southern Ocean is a key player in the global thermohaline circulation. The Southern Ocean overturning circulation functions as a massive pump, driving cold water to the deep ocean and distributing oxygen-rich water to other parts of the ocean. Additionally, the Southern Ocean serves as a vast reservoir of carbon dioxide. It absorbs a significant portion of atmospheric CO2, playing a crucial role in slowing down climate change. On the opposite side of the Earth, the Arctic Ocean encircles the North Pole, the coldest place on the planet. With an area of 14.06 million square kilometers, it is the smallest of Earth's 5 oceans. Yet it remains a crucial link in the global climate regulation system. Here, slow-moving ocean currents flow beneath thick layers of ice, while winds from the Arctic sweep southward, shaping the climate of half the planet. All 5 oceans together form the largest ecosystem on the planet. According to IPBES, at least 2.2 million species are estimated to exist in the world's oceans. However, only about 240,000 species have been officially described so far. More than 90% of all habitable space on Earth lies beneath the ocean's surface. Below, coral reef ecosystems, though covering only 0.1% of the ocean's area, support 25% of all marine species. Over 33,000 species of fish swim through the oceans, making up about 50% of all vertebrate species on Earth. More than 130 species of marine mammals, from the smallest creatures to the largest giants, inhabit these vast waters. They play a vital role in the ocean ecosystem, not only maintaining the balance of the food chain, but also contributing to the natural carbon cycle. According to a 2024 NOAA study, marine mammals can absorb tens of millions of tons of carbon dioxide per year, storing it within their bodies and helping to mitigate the impacts of climate change. The ocean's surface unfolds like a giant mirror, reflecting the sunlight and the ceaseless movements of the aquatic world. This is the boundary between two worlds, where the atmosphere meets the sea. Creatures that live on the surface, known as neuston, form a tiny yet essential world within the marine food chain. Golden sargassum seaweed drifts across the ocean, creating the Sargasso Sea, a shoreless expanse where thousands of species depend on it for survival. In these open waters, floating barnacles cling tightly to drifting seaweed, marine snails glide along the currents, and nudibranchs move slowly through the waves. Cnidarians, with their delicate flowing tentacles, float on the surface like fragile petals, yet conceal the electrifying power of static discharge. Just beneath the clear ocean surface, the ocean sunfish drifts lazily, basking in the sunlight, as if simply lying there to soak up the warmth. This unique behavior is the reason behind its English name, sunfish. Scientists believe that this habit helps it regulate body temperature after deep dives, or allows seabirds like seagulls and frigate birds to clean off parasites from its skin. Other hypotheses suggest that sunbathing allows it to absorb heat quickly, restoring energy before resuming its deep-sea hunting journey. The ocean sunfish is an opportunistic carnivore, feeding mainly on small fish, fish larvae, squid, and crustaceans. It can also consume eelgrass, taking advantage of food sources across different ocean layers, from the surface waters down to the seafloor in certain regions. Though it spends much of its time near the surface, the ocean sunfish does not limit itself to shallow waters. Adult individuals frequently dive below 200 meters, and at times they have been recorded descending as deep as 600 meters in search of food. However, they have a clear temperature limit. If trapped in waters below 12 degrees Celsius for too long, they may become disoriented, weakened, and ultimately unable to survive. Larger than the sunfish is the basking shark, the second largest shark in the world. They can grow up to 7.9 meters long, with a massive body and an enormous mouth wide enough to engulf an entire stream of water. When summer arrives, ocean currents bring plankton-rich waters toward the coast. Basking sharks appear near shore, sometimes even venturing into narrow bays and brackish waters. Here, they swim with their mouths wide open, using their huge gill rakers to filter out every tiny organism drifting through the water. A 5-meter-long individual can filter up to 450 tons of seawater per hour, capturing millions of copepods in a single sweep. When necessary, they can dive to over 910 meters, taking advantage of deeper water layers to find food during winter. In the cold months, when surface plankton declines, basking sharks do not hibernate like many other fish, but instead continue their journey into the deep sea. There, overwintering zooplankton still thrives, serving as a critical food source. The true apex predator of the ocean is the great white shark. It is one of the most infamous hunters of the sea. An ancient warrior that has survived millions of years of evolution, carrying the legacy of its ancestors from the time of Megalodon, yet it does not need enormous size to claim its place as the ocean's ruler. Great white sharks can travel thousands of kilometers on unpredictable journeys. Individuals off the coast of California have been tracked swimming as far as Hawaii. Others migrate from South Africa to Australia. No one truly knows where they go during winter, only that they always return, following a cycle etched into their instincts over millions of years. They roam across temperate and tropical waters, appearing along the California coast, in the cold waters of South Africa, from the shores of Japan to the remote islands of Australia. They are not bound by any ocean, not restricted by any borders. There is only one rule that governs their journey: find the most energy-rich prey to survive. Ocean currents carry pinnipeds, seabirds, fish, and at times, whale carcasses, perfect feasts for the great white shark, a predator that knows no hesitation or doubt. Great white sharks do not rely solely on speed and strength to hunt. They have a secret weapon, ampullae of Lorenzini. A network of electroreceptors that allow them to detect the heartbeat of prey, even if it is buried beneath the ocean floor. Even in total darkness, even when visibility is blocked, a single electric pulse is all they need to pinpoint their target with near-perfect accuracy. Their muscular structure enables them to reach speeds of 40 kilometers per hour, faster than any seal. With over 300 serrated teeth arranged in multiple rows, they constantly replace lost or broken teeth, ensuring that every bite can pierce through the thick hides of large prey. When hunting, the great white shark strikes from below, launching itself with a bite force of 18,216 newtons, crushing bones and muscle in an instant. Its jaws deliver the second most powerful bite force in the animal kingdom. But do you know which creature surpasses it? Drop your answer in the comments. For northern elephant seals, massive prey that can outweigh the shark itself, the great white does not rush to finish the hunt. A single bite to the lower body immobilizes the seal, robbing it of its ability to swim away. Blood seeps into the water, signaling to the shark that it only needs to wait. The prey will weaken and eventually succumb. But the great white shark does not always hunt. When a whale carcass sinks into the depths, the scent of its blubber spreads through the water, drawing sharks from kilometers away. This becomes a feast that lasts for weeks, where a 4.5-meter-long shark can survive for 1.5 months on just 30 kilograms of whale fat. No energy wasted, no risk taken, just taking advantage of what the ocean provides. Yet, even the top predator has an enemy. When a larger shadow glides through the water, the balance of power shifts instantly. Even the great white shark knows it is no longer the ruler. The only predator capable of hunting the great white shark is the orca. This is the apex predator of the ocean, possessing strength, intelligence, and top-tier hunting strategies, whether hunting alone or in groups. When an orca detects a great white shark, it does not attack recklessly. Instead, it surrounds the shark, cutting off all escape routes, circling persistently to exert psychological pressure. When the moment is right, it dives beneath the shark and rams upward, flipping it upside down with precision. In this state of tonic immobility, the shark becomes completely paralyzed, unable to resist, its body floating helplessly in the cold water. The orca's sharp teeth may not have the crushing bite force of a great white, but they strike with deadly accuracy, targeting the liver, which is packed with high-energy fats. Within minutes, the shark is torn apart, and the orcas silently depart, leaving behind a chilling void. After an orca's relentless hunt, great white sharks disappear from the area for months, as if they understand that the ocean is no longer safe. If any creature embodies curiosity and remarkable intelligence, it is the orca. They do not just hunt. They play, communicate, and can even learn the vocal dialects of different orca pods. With a 5.4-kilogram brain, the largest of any marine animal, they do not rely solely on instinct. They strategize, learn from one another, and pass down hunting techniques from generation to generation. The fearsome power of an orca does not lie in its strongest bite or its fastest speed. It lies in its flawless precision. Rather than relying on brute force, orcas use echolocation, emitting sound waves and analyzing the echoes to pinpoint prey, even when hidden in darkness or beneath ice sheets. With a top speed of 56 kilometers per hour, faster than any shark, they can chase down nearly any prey in the ocean. Orcas are not just lone hunters, they are highly social creatures. They live in matrilineal groups where females remain with their mothers for life, forming stable family pods that last for generations. A single pod can consist of 5 to 40 individuals, with the oldest female acting as the matriarch, leading the group in migration and hunting. Some pods can exist for over 90 years, with up to 4 generations living together, a rare phenomenon in the animal kingdom. These pods are not randomly formed. They have tight-knit social structures, with clear role divisions, coordinated hunting strategies, and strong family bonds, deeper than any other oceanic species. Every orca pod has its own unique hunting techniques, passed down through generations. Pods that hunt salmon in Norway have social structures similar to those that hunt herring. However, in Argentina and the Crozet Islands, they operate under a transient model, where individuals separate from the pod temporarily to hunt seals and dolphins. Some pods have diverse diets, consuming fish, seabirds, and even whales, while others specialize in specific prey, never leaving their designated hunting grounds. Beneath the rolling waves of the ocean, where sunlight still flickers through the surface, lies a completely different world. A world where humans have never truly set foot, where absolute darkness reigns, temperatures drop near freezing, and crushing pressure weighs down on all life. The deep sea, occupying 95% of the habitable space for marine life, is the deepest layer of the planet's waters. Alongside the sea floor, these regions make up 98% of the ocean's area, yet they remain one of Earth's greatest mysteries. From depths of 200 to 1,000 meters lies the mesopelagic zone, where sunlight cannot reach. Here, the megamouth shark, using a vertical migration strategy, moves from depths of 1,000 meters up toward the surface at night to hunt. They use bioluminescence from their bodies to lure prey. Sightings of this species are so rare that only about 100 specimens have ever been recorded, making it one of the most mysterious sharks in the world. Deeper still, the ocean expands into total darkness. The bathypelagic zone, ranging from 1,000 to 4,000 meters, maintains a constant temperature of 0 to 4 degrees Celsius. While pressure is so extreme, it can crush any organism that isn't adapted. Creatures here have no choice but to generate their own light through bioluminescence. Descending further, the abyssopelagic zone stretches beyond 4,000 meters. No light ever reaches this realm, only icy cold and creatures that have evolved to endure extreme pressure, hundreds of times greater than at the surface. Slow-moving currents carry tiny organic particles from the upper ocean, forming a type of marine snow. This delicate shower of nutrients serves as the only food source for most deep-sea life, where survival is completely independent of photosynthesis. At the deepest ocean trenches, the hadalpelagic zone extends from 6,000 to 11,000 meters. The Mariana Trench, the deepest known point on Earth, plunges 10,994 meters below sea level. Here, the pressure is over 1,000 times greater than at the surface, forcing every organism to evolve in unique ways. No rigid bones, no gas-filled swim bladders. Only soft, flexible bodies can withstand the relentless compression of this extreme world. Life in the deep sea does not merely survive, it thrives in ways that defy expectations. Creatures living near hydrothermal vents do not rely on sunlight, but instead harvest energy from sulfur-rich plumes, reaching temperatures of 400 degrees Celsius, erupting from cracks in Earth's crust. These tiny ecosystems can endure for centuries, sustaining species unknown to humanity in one of the planet's last unexplored frontiers. Silently lurking among rocky reefs and kelp forests, the giant Pacific octopus glides across the seafloor. Each tentacle gently brushes against the soft sand, sensing the vibrations of the world around it. They are the masters of camouflage and strategy in the deep sea. Evolving over millions of years, this creature possesses a highly flexible body, capable of squeezing into any crevice no larger than the size of its eye socket. In the cold waters of the North Pacific, from Alaska's edge to depths of 2,000 meters, the giant Pacific octopus remains hidden in the shadows, waiting for the perfect moment to strike. Its long tentacles, lined with powerful suction cups, are always ready to seize prey in an instant. The giant Pacific octopus is one of the largest cephalopods, reaching an arm span of 9.8 meters and weighing over 270 kilograms. But beyond its impressive size, its large brain contains over 300 million neurons, not just in its head, but spread throughout its tentacles, allowing each arm to process information independently. Each tentacle can think for itself, make decisions, and react on its own without needing signals from the central brain. The giant Pacific octopus can learn to unscrew bottle caps, use tools, and even memorize escape routes in a maze. In captivity, some individuals have dismantled expensive equipment, opened tank valves to escape, and even recognized specific staff members in laboratories. Hidden in the deep, the giant Pacific octopus spends most of its time in darkness, only moving when necessary. It blends seamlessly with coral reefs, changing color and skin texture in less than a second. When the time comes, it bursts from its hiding place with incredible speed. With a powerful jet-propelled burst, it launches forward, expelling water through its siphon for rapid movement. But when it doesn't need to rush, it simply crawls across the sand, leaving behind subtle trails, visible only to the most experienced predators. Hunting is not a chase. It is a game of strategy and precision. The giant Pacific octopus approaches its prey with extreme caution. Its tentacles extend, delicately tracing the hard shell of a crab or lobster, sensing even the smallest movements. Once the prey is within reach, it tightens its grip with immense force. Its suction cups latch on, leaving the prey no chance of escape. Within seconds, a potent neurotoxic venom is injected, paralyzing the prey and dissolving its internal tissues inside its hardened shell. A creature once protected by armor is now reduced to an effortless meal. Beyond crabs, shrimp, scallops, abalones, snails, and clams, the giant Pacific octopus has been observed hunting small sharks. In octopus middens, piles of leftover shells and bones from previous meals, scientists have discovered shark remains. This is undeniable evidence that this predator is unafraid to challenge even formidable hunters when necessary. Deeper still, at the ocean floor, where nutrients are scarce, life persists through three primary energy sources: marine snow, chemosynthesis from hydrothermal vents, and cold seeps. Among them, the most remarkable is the death of a whale, whale falls. When a whale dies, its life does not end. Instead, it becomes the foundation of an entirely new ecosystem. When a whale dies, its body sinks to the ocean floor like a meteorite, falling into eternal darkness. A massive, fat-rich carcass, containing hundreds of tons of organic material, now becomes the center of a rare gathering. Its signal travels through the cold ocean currents, triggering a biological wave in the deep sea. From afar, marine scavengers sense the opportunity for survival. The feast begins. The scent of decay drifts through the cold currents, stretching for kilometers, seeping into the highly sensitive olfactory system of the Greenland shark. These sharks are the longest living vertebrates ever recorded. Radiocarbon dating on their eye tissue has revealed that their average lifespan is at least 272 years, with the oldest individual estimated to be nearly 400 years old. This means that some Greenland sharks were born when the first sailing ships crossed the Atlantic Ocean, existing for centuries before humans even began to understand their existence. The Greenland shark does not need eyes to find its prey. Its vision has nearly deteriorated, as its corneas are often infested by the parasitic copepod Omatocoita elongata, which clings to its eyes for years. Instead, it relies on its sense of smell, detecting even the faintest vibrations in the water. Alongside the deep-sea sharks, Japanese spider crabs patiently wait. They cannot compete with sharks or hagfish, but they are perfect scavengers, cleaning up the final remains. With legs stretching up to 3.6 meters, thin yet powerful, they reach out like giant arms, searching for even the smallest scraps in the darkness. As muscle fibers and tissue fragments drift down, the spider crab quickly seizes them, carefully cutting each piece apart with its sharp pincers, turning whatever remains into a valuable source of nourishment. A whale carcass provides more than just food. It becomes a shelter, a temporary yet resource-rich ecosystem. Smaller crustaceans are drawn to the whale's decomposition, and the Japanese giant spider crab takes full advantage of this. It remains motionless, waiting in silence, then suddenly strikes, snatching up an amphipod or a wandering fish that drifts too close, turning them into an extra meal. After the mobile scavenger stage, when the whale carcass is no longer a solid mass of flesh, the large scavengers depart, leaving behind a bare skeleton resting on the cold seafloor. The opportunistic stage does not unfold with the same chaotic frenzy as before. Life now moves at a slower rhythm, as smaller, more persistent organisms take over the abandoned feeding grounds. This stage can last anywhere from a few months to 4.5 years, depending on whale size and environmental conditions. The whale's nutrients are no longer just in the bones. They have already seeped into the surrounding sediment, creating a nutrient-rich layer where bacteria thrive. Thin biofilms begin to coat the whale bones, turning them into living structures rather than just remnants of the past. Slow-moving sediment feeders arrive, consuming organic matter that has settled within the deep-sea mud. During this stage, the fangtooth moves silently across the muddy seafloor, slipping between the cold, pale bones of the whale skeleton. Its body, no longer than 16 centimeters, appears crushed by the immense pressure of the deep sea. Yet it possesses one of the most terrifying jaws in the abyss. Its oversized fangs jut out from its mouth, so sharp that when it closes its jaws, the teeth must fit into special grooves in its skull to prevent them from piercing through its own flesh. The fangtooth does not need large meals, only the tiny scraps left behind in the opportunistic stage of the whale fall. Here, food is no longer abundant, but for those patient enough, survival is still possible. As the whale skeleton becomes fully coated in bacteria and other scavengers begin to move on in search of new feeding grounds, the fangtooth remains. It feeds on tiny remnants trapped within the bone crevices, on the microscopic particles overlooked by larger creatures. It does not require much, only enough to last through the coming months, until another whale fall occurs, until the cycle begins again. After the opportunistic stage, the sulfophilic stage begins. On the bare skeleton of the once massive whale, a microbial ecosystem takes over, extracting the last remnants of energy from the bones to sustain life in eternal darkness. The whale's nutrients no longer exist as meat or fat. Now they have seeped deep into the dense bone structure, becoming fuel for a chemical transformation that will last for decades. Anaerobic bacteria begin breaking down the remaining lipids within the bones, producing hydrogen sulfide, a toxic compound for most creatures, but the foundation for an entirely new ecosystem. Whale bones can contain 4 to 6% lipids by body weight. This residual fat allows the sulfophilic stage to last between 50 and 100 years. During this period, bacteria continue decomposing organic matter in the bones, creating a chemical environment similar to hydrothermal vents and cold seeps, where life thrives without sunlight. The whale skeleton gradually becomes a part of the deep sea floor. As the last reserves of lipids within the bones are exhausted, the hydrogen sulfide-rich environment begins to fade. The sulfur-loving bacteria slowly disappear, making way for more typical deep-sea organisms. The skeleton is no longer a source of energy, but rather a permanent structure, settling into the soft sediment of the abyss. At this point, the whale fall transitions into its final stage, the reef stage. No longer serving as a food source, the whale's skeletal remains now act as an artificial reef. It can persist on the seafloor for 100 to 1,000 years, depending on environmental conditions. During this time, it provides a solid foundation in an otherwise soft, muddy environment, attracting a wide range of marine life. At the farthest reaches of the ocean, evolution has turned the impossible into reality, forcing life to adapt to the harshest environment on Earth. There is no sunlight, no photosynthetic plants, only eternal darkness, freezing temperatures, and immense pressure. Yet life persists, finding ways to thrive in ways unseen anywhere else on the planet. The deep ocean floor remains largely unexplored. In 2023, the Schmidt Ocean Institute discovered hundreds of new species at depths of over 4,000 meters. This proves that even in the most desolate parts of the ocean, life continues to be a crucial part of Earth's vast ecosystem. However, life on the seafloor cannot survive without unique energy sources. With no plants and no photosynthesis, deep-sea ecosystems rely on nutrient flows from the upper layers of the ocean. The primary source is marine snow, a slow descent of organic particles including dead organisms, decaying algae and bacteria, drifting from the surface to the ocean depths. This biological snowfall moves gradually through the water column, carrying fragments of life to the pitch-black abyss, where it sustains countless deep-sea species. Under the immense pressure of the deep sea, where only the faintest traces of light filter down from the upper layers, a silent predator drifts through the water, unhurried, making no sound. This is one of the few species known for intrauterine cannibalism, where the first shark embryos to hatch inside the womb begin hunting and consuming their unhatched siblings. Only one survivor from each uterus will make it to birth, stronger, with more developed jaws, already prepared for the harsh world of the deep ocean. Beyond the nutrient flows from upper waters, certain areas of the sea floor host unique ecosystems, completely isolated from what happens at the ocean's surface. These are hydrothermal vents, natural chemical reactors that erupt superheated, mineral-rich water into the deep sea. They form along mid-ocean ridges, submerged mountain chains stretching over 60,000 kilometers, where tectonic plates slowly pull apart, allowing magma from the Earth's mantle to rise. Although hydrothermal vents make up only a tiny fraction of the deep-sea ecosystem, they play a crucial role in maintaining the ocean's nutrient cycle. The compounds released from these vents provide energy for deep-sea organisms and influence the chemical balance of the ocean on a global scale. When cold seawater seeps through cracks in the ocean crust, it gets superheated to temperatures reaching 400 degrees Celsius, then rises back up, carrying dissolved minerals from the Earth's interior. As these superheated fluids meet the frigid 2 degrees Celsius seawater, minerals like sulfides, iron, manganese, and zinc rapidly precipitate, forming massive black or white plumes, known as black smokers and white smokers. Over time, these mineral-rich structures grow into towering chimneys, transforming into deep-sea skyscrapers where life thrives in unimaginable ways. The hydrothermal vent waters carry hydrogen sulfide and methane, compounds toxic to most life, yet they serve as an invaluable energy source for chemosynthetic bacteria. These bacteria thrive on the hair-like setae covering the Yeti crab's claws, absorbing chemical compounds and converting them into organic matter. When the time is right, the crab simply scrapes the bacteria off with its claws, feeding itself effortlessly. No hunting, no searching, just harvesting its own microbial farm. The Yeti crab, a tiny but extraordinary creature, was discovered in 2005 near hydrothermal vents off Antarctica at a depth of 2,200 meters. Beyond its unique survival method, the Yeti crab knows how to position itself strategically around the vent openings, seeking areas rich in minerals to help its bacteria flourish. If a vent weakens, the crab gradually migrates, searching for a new hydrothermal source before it's too late. Recent studies suggest it can detect chemical shifts in the water, allowing it to identify locations with the ideal concentration of compounds needed to sustain its bacterial fields. Unlike the violent plumes of hydrothermal vents, cold seeps do not erupt with boiling water. Instead, methane and hydrogen sulfide seep out slowly from the Earth's crust, creating a strange world where life thrives without the need for sunlight. Cold seeps emerge along continental margins, and deep ocean basins, where methane trapped in sediment for thousands of years begins to leak due to shifting pressure. These gases are not always visible, but they leave clear traces behind. On the seafloor, unusual mud formations rise to the surface, while towering carbonate chimneys form from minerals precipitated by the reaction between methane, hydrogen sulfide, and seawater. These gases seep through the cold seabed, creating an entirely different ecosystem, where organisms have learned to survive through chemical reactions rather than sunlight. The temperature at cold seeps is much lower than at hydrothermal vents, usually ranging between 4 and 10 degrees Celsius, yet they are hotspots for deep sea life. Creatures here rely on chemosynthesis, a process where energy is extracted from chemical compounds like methane and hydrogen sulfide. Methanotrophic and sulfur-oxidizing bacteria act as biological power plants, converting toxic compounds into nutrients that sustain entire deep-sea ecosystems. Organisms living here must adapt to a methane-rich environment where oxygen is often scarce and seawater acidity is higher due to ongoing chemical reactions. Some mollusks form symbiotic relationships with chemosynthetic bacteria, extracting energy from methane instead of consuming food. Certain species lack mouths or digestive systems entirely, surviving solely through their symbiotic bacteria. Tiny crustaceans roam across the methane-rich sediment, while predatory fish lurk silently within carbonate reefs that have formed over centuries. Cold seeps are not just home to bizarre life forms, but also play a crucial role in the global carbon cycle. The compounds escaping from the seafloor can be absorbed by methanotrophic bacteria, helping to regulate methane levels in the ocean and atmosphere. Without this process, seafloor methane leaks could accelerate global warming, as methane is 25 times more potent as a greenhouse gas than carbon dioxide. The cold seeps are not silent realms. This is the territory of the chimera. It hovers in the water column, its eyes locked onto the sediment below, detecting the faintest vibrations of prey moving unknowingly. The chimera, also known as the ghost shark, is a wanderer of the abyss, a living witness to hundreds of millions of years of evolution. Beneath the rolling waves, in the shadows of submerged mountains and desolate ocean floors, marine life continues to endure. They do not fight with claws or fangs, but with resilience and adaptation. But this time, their greatest threat is not another predator, it is a far greater force, the changes driven by humanity. Climate change is no longer a distant possibility, it is a reality. At the ocean surface, coral reefs are losing their brilliant colors, their branches turning ghostly white, like skeletons beneath the sea. As ocean temperatures rise, zooxanthellae, the symbiotic algae that provide corals with energy, are expelled from their hosts, causing corals to slowly wither away in a process known as coral bleaching. Hundreds of species of fish, crustaceans, and mollusks, once dependent on coral reefs for survival, are now disappearing, forcing larger predators to search for new hunting grounds. Farther out, where cold currents meet warm waters, large predators like the great white shark are being forced to alter their migration patterns in search of food. In the Arctic Ocean, sea ice is melting faster than ever, disrupting the delicate balance of an ecosystem that has existed for millennia. Even the deep sea dwellers, like the Greenland shark, can sense the change unfolding. Deep sea mining, the extraction of minerals from the ocean floor, is now intruding upon ecosystems that humans have only just begun to explore. Hydrothermal vents, the lifeblood of deep-sea energy cycles, could be destroyed by industrial machines, tearing apart ancient landscapes that have fueled life for millions of years. The creatures that have survived off Earth's energy for millennia could vanish before humans even understand their existence. Cold seeps, where methane and hydrocarbons seep from the ocean floor, are also at risk. Deep-sea oil and gas extraction could disrupt the natural cycles of the ocean, altering the chemical flows that creatures like the chimera rely on for hunting and survival. These small shifts could set off a chain reaction, affecting an entire ecosystem in ways that humans cannot control. Meanwhile, overfishing is driving countless marine species toward critical population declines. Orcas are being forced to hunt farther from home due to the disappearance of salmon populations. Sand tiger sharks are losing their natural prey as smaller fish populations are depleted by excessive fishing. And in the deep sea, species that depend on whale falls may soon lose their vital food source as whale populations decline due to illegal hunting and ocean pollution. The question remains: amid the unpredictable changes in the marine ecosystem, can the great creatures of the deep continue to adapt as they have for millions of years? Deep within the ocean, the answer has yet to be written. But if we do not act now, there may come a day when the story of the deep sea exists only in faded pages, telling of a time when the ocean was whole, abundant, and full of mystery. Amid these challenges, scientists, governments, and environmental organizations are racing to save the ocean. The Ocean Cleanup, a Netherlands-based environmental technology organization, has deployed large-scale plastic collection systems, removing hundreds of tons of waste each year from the Great Pacific Garbage Patch. Bleached coral reefs are being revived through restoration projects like Ocean Ecostructures, which develops artificial reef systems that mimic natural structures to attract marine life. Bio-boosting system technology is being implemented, enhancing coral resilience against climate change. Stronger policies are also being enforced. Marine protected areas are being expanded worldwide to cover at least 30% of the ocean by 2030. In the deep sea, cold seeps and hydrothermal vents are now being protected from deep sea mining threats. New research from the IPCC indicates that limiting deep sea mining could reduce biodiversity loss risks by 30% in the deep ocean. But is this enough to prevent an ecological crisis? Conservation efforts from organizations and governments alone are not enough without individual action. We can start with small but meaningful changes, reducing single-use plastics, participating in beach cleanups, and supporting eco-friendly products. We can choose sustainable seafood, reduce waste, and raise awareness in our communities. The ocean has sustained us. Now it is time for us to protect it before it is too late. If you have ever gone diving and witnessed the ocean's extraordinary creatures, don't hesitate to share your knowledge and experiences in the comments below. Your stories can serve as inspiration and motivation for conservation efforts, preserving rare wildlife and ecosystems for future generations. Don't forget to like, subscribe, and turn on notifications so you can join us on the next incredible adventure. Or continue exploring the wild survival stories of other regions in the Antarctica. Survival in the realm of giants, or wild Yellowstone, ruthless predators and majestic wilderness.